Algebra 1. Here is your video for 12.4, and we last talked about multiplying rational expressions, so it makes sense that in this video we're going to talk about dividing rational expressions. And there's nothing new in this section as long as you remember the trick to dividing fractions, because if we can divide fractions, we can divide any expressions that are part of fractions. So if I give you this, a divided by b divided by c divided by d, or this fraction divided by this fraction, you should remember the keep, change, flip method. So the keep means we're just going to leave the first fraction alone. We're going to change the division symbol to multiplication, and then we are going to flip the second fraction. So instead of having c over d, we're going to have d over c. And then to multiply fractions, just like we talked about in our last video, you're going to multiply across the top. Here, let me get this arrow. So it'd be a times d, and multiply across the bottom, which becomes b times c. Should be nothing new. So, since we're converting division into multiplication, as soon as you do the keep, change, flip, you apply everything from 12.3. So this should just be a review of last video. Hopefully, it'll be kind of a nice little break here. So, we're going to keep that first fraction the way it is, divided by 5a squared b squared. I'm going to change my sign, and then I'm going to flip. This is going to be 10ab divided by c squared d squared. And then multiplying across, one of the methods I talked about in the last video was that cross reducing. So I'm personally going to do that right now. I've got a c squared over a c squared. That's just a fancy 1, so I'm going to reduce it. And then I've got some other stuff going on. There's definitely a single d up here. There's 2 down here. When I cancel one of those out or reduce, I just get rid of this one, keep a single d on the bottom there. And then let's work this way as well. 10 divided by 5, ignoring this 12 because we can't reduce 12 over 5. But 10 over 5 is the same thing as 2 over 1. So when I multiply here, instead of multiplying 12 times 10, it's a little bit easier because I only have to do 12 times 2. All right, 1a up here, 2a is down here. That means one of these cancels. I'm left with just 1. Same thing with b. This cancels, and I'm just left with a single down there. So 12 times 2 is 24 on the top. No variables left over here. On the bottom, we've got 1 times a times b times d. I don't even have to write the 1 because we're just multiplying. And I can't simplify any further, so that's my final answer. All right, remember, if we have trinomials, before we can actually do anything with them or multiply or anything, I like to simplify them. I like to break them down into their parts. So this x squared plus 6x minus 27, I'm going to keep this fraction the way it is, but in the process of keeping it, I'm just going to break it down into its parentheses. So, no x out front, no need for the x puzzle. I didn't leave myself much space there. 27, that'd be 3 and 9. 3 and 9. Which one needs to be negative? That would be the smaller one. So there's the top. Same thing with the bottom. Give myself a little more space at that time. Again, no need for an x puzzle. 18 would be 9 and 2 to add to that 11. They're both positive, so both of these are going to be positive. Now I'm going to do the same thing over here, but I'm going to change the sign in the middle, flip this fraction. So now, when I am factoring the bottom, whatever I'm factoring with the bottom is going to go on top, and then because I can't factor the top, I'm just going to go ahead and move that down to the bottom right away. All right, let's factor this out, though. We've got an x and an x. The only thing that can multiply to 2 is a 1 and a 2. To get a positive number in the middle, I have to be positive 2 and a negative 1. All right, let's start cross-reducing. We're multiplying across. So I've got an x plus 2 on the top. I've got an x plus 2 on the bottom. So those cross-reduce to be 1. I've got an x minus 3 on the top and an x minus 3 on the bottom, so those cross reduce to be 1. I have an x plus 9 on the top and an x plus 9 on the bottom, those cross reduce to be 1. And now I am left with only an x minus 1 on top and a 1, imaginary 1 on the bottom. So when I simplify this, I get x minus 1 divided by 1, or just x minus 1. That is a beautiful example of how algebra can take something super large and challenging and turn it into something much more manageable and nice to look at. All right, let's keep going here then. These are a few more examples. After 2 examples, I'd like you to pause the video here. Go ahead and give these 3 a try, including this challenge. Go ahead and give it a shot, see if you can follow the previous 2 examples we talked about. And once you've done that, come on back, we'll do them together. All right, hopefully you paused that video long enough to give these a shot. Now we're going to work through them. 12ab over a squared b squared. Keep the first, change the sign, flip the fraction, and simplify. B up here cross reduces, a up here cross reduces. This leaves me with just a single a down on the bottom. I've got another a over here, so I can even cross reduce with that one. Nothing else to really simplify, so I now have 12 on top over b squared on bottom. Next one, keep the first, but I'm going to factor it. Leave that bottom part alone. X, all right, 6 would be 3 and 2 or 5 and 1. But the only way to get a negative 5 would be with the 3 and the 2, where both are negative, to multiply to that positive 6. Change the sign, and then flip the second fraction, x minus 3. I've got that on top and bottom. I'm going to cross reduce those to 1. 15 divided by 5 cross reduces to 3 over 1. And I can't simplify anything else. So let's go ahead and multiply. 3 times x minus 2. I'm going to go ahead and just distribute that in. I guess I'll show you this step first. 3 times x minus 2 over 1. I'm going to distribute it in to make it look a little bit nicer because it's only one term. It's not a fraction. 3x minus 6. Boom. Just like that. All right, and that challenge problem, we've had a few of these on the last page, so stay with me. Keep the first. As I'm factoring the top, I notice right away it's a difference of squares. Square, square difference. So that becomes a minus 3, a plus 3. Factoring the bottom, that is going to involve an X puzzle. I'm not going to show that in this video. If you would like to see that worked out, go ahead and send me a quick email. But otherwise, I'm just going to tell you that I can factor this in my head. It's going to be that factored. Change the sign. And then flip that second fraction. Running out of room here. A plus 3 can't be simplified anymore, so that's just going to hang out on the bottom here. But 4a squared minus 1 is a difference of squares. Not sure if you recognize that. It's a difference of squares to 2a minus 1 and 2a plus 1. I know I'm going off here a little bit. All right, now that we've got everything set up, let's cross reduce. 2a minus 1 down here is the exact same as 2a minus 1. Those cross reduce. Got an a plus 3 and an a plus 3. And then everything else is a singleton. So let's move that down to the bottom. A minus 3 times 2a minus 1. I like to put the term with the biggest coefficient out in front. It doesn't really matter because it's multiplication. And then a plus 7 on the bottom. There you go. But we are not done. We are now going to jump to the back where we're going to do something very, very similar to this. It's just got a little bit different name and it's more of a real world application. So this is called dimensional analysis. This is used a lot in your chemistry classes and other science classes, so it's a great skill to have, but it's also very useful in math. So dimensional analysis is just the project or the task of dividing rational expressions that involve units of measure. So instead of just working with numbers, we've now got some units to work with. So let's look at this first example. A speed skater skated 100 meters in 1.14 minutes, and it asks us to find his speed in kilometers per hour. So the way that I like to set up my dimensional analysis problems is this. I first write out the fraction that I have to start out with, and that would be 1,000 meters per 1.14 minutes. Got to be careful with your units here because meters and minutes can get a little confusing. This is where I'm starting. I also like to give myself an end goal. So when this says I want to find the speed in kilometers per hour, what I like to do personally is I go to the other side of my paper and I say I want kilometers, or km, per hour. So I'm starting out with m over min, but I eventually want to get to km over hr. Well, how are we going to do that? That is the dimensional analysis. Our first task is we need to transform these units into these. So let's do that. If I want to go from minutes to hours, notice my minutes is on the bottom and I need hours to be on the bottom. The way that I'm going to do this is I am going to convert minutes on top. How many minutes per hour? Well, we know there are 60 minutes in 1 hour. So I have essentially said one way to go from minutes to hours and to cancel my minutes, to cross-reduce those, is to transfer like this. But now that I have this new fraction set up, what am I going to do with it? Well, I'm going to multiply, because this allows me to cancel and cross-reduce. Just like we were canceling and cross-reducing using multiplication before, we're going to continue that. So I've now got my minutes changed into hours. Boom, checked off. It's on the bottom where it's supposed to be. It's on the bottom where it's supposed to be. They match up. But I can't just multiply by this because I'm still in meters. So what I'm going to need to do is multiply by another adjustment. And that adjustment needs to take me from meters up to kilometers. I need kilometers on top, and I need meters on bottom because that's the only way I can get the top and the bottom to reduce. Now, how many meters are there in a kilometer? Well, if you don't know off that the top of your head, that's okay. I'll let you know that there is, in fact, 1,000 meters in a kilometer. Now, look at this. Our units have cross-reduced to only leave us with numbers. Now I can calculate with numbers and only be left with the 2 units that I need. If I've done my dimensional analysis correctly, I will only be left with the units I want. If they're in the wrong place, you need to go back, sorry about that. You need to go back and make sure that you've positioned everything correctly to cross-reduce. So now that I've got my units, kilometers and hours, all I'm going to do is multiply across. I have 1,000 times the 60, and I have 1 times 1,000. But one of the cool things about this is that the same way that units will cancel out, so will numbers if they're divisible. So I could divide 60 by 1,000, but even easier, I forgot this 1.14 over here. Whoopsies. I can either multiply across first, or I can cancel to make things easier on myself. So for example, 1,000 divided by 1,000 is just 1. So those cross-reduce, making my multiplication quite a bit easier. Now I just have 60 times 1 over 1.14 times 1. And technically these 1's cancel out too if you like that, but you don't have to. excuse me, I'm now left with 60 divided by 1.14. If I put this in a calculator, this is equal to approximately 52.6 kilometers per 1 hour. And you have now converted his initial rate into kilometers per hour through dimensional analysis. That was a big example to start off with. Let's see another one. If I start off with 144 inches cubed and I want to go to feet cubed, I'm going to do the same thing. This one already gives me my starting and my ending, so I'm not going to rewrite it the same way I did the kilometers per hour example. I'm actually going to go right into 144 inches cubed, and then I'm going to say per 1. It doesn't give me a second unit, so if I need to write it as a fraction, I know any number can be written as itself divided by 1. Another way you may see dimensional analysis done without fractions is in a table form, and I'm going to show you that one now. Instead of doing these little multiplication signs in the middle, I'm going to separate my units with lines and just say that each one is its own separate box. Because you know if you're multiplying, you're going to multiply everything on the top anyway. So instead of having a multiplication sign, we just say line. Now I need to convert from cubic inches on top to cubic feet on top. And I need to know how many cubic inches there are in a cubic foot. Again, not a super common thing to know, so I will go ahead and tell you that it is 1,728 cubic inches in 1 cubic foot. Now, I'm going to double check myself. I notice my inches cubed, or my cubic inches, cancel out. My ones cancel out, and I'm left with just numbers and the only label that I want left over. Now I'm simply going to multiply across the top to get 144 feet cubed over 1,728. Notice there's no label on the bottom, so I don't need one on the bottom. To make this a little easier to look at, I am going to divide it and find that 144 cubic inches is approximately the same as 0.083 repeating cubic feet. And that's my answer. All right, if you're feeling up for it, go ahead and try this one on your own. If not, let's work through one more together and then you can try the last one on your own. All right, let's see what's going on here. Express $4.48 per pound in dollars per ounce. All right, starting $4.48 per 1 pound. Hopefully everyone knows that LB is short for pound. And I'm going to dollars per ounce. So dollars on top, ounces on bottom is where I'm headed. I like to give myself a goal. Now notice something. My top unit is going to say the same. I don't have to convert my dollars. I only need to convert pounds to ounces. So that actually takes one step away. I don't know which method you prefer. I think I prefer the table method, but for right now I'm going to continue using the multiplication signs. I know that I need to go from pounds to ounces, and I need ounces to end up on the bottom. So that's where I'm going to put it, and that's okay because pounds is going to cancel out on top. Pop quiz, how many ounces are there in a pound? Maybe you knew it, maybe you didn't. That's okay. In 1 pound, there are 16 ounces. All right, let's do that cross-reducing. The ones cancel, the units cancel, and when I find out, I still have 448 on top, but I now have 16 ounces on bottom. That's okay because those are what I want my units to be. Now I just have to do the math behind it. 448 divided by 16 ends up being approximately 28 cents or $0.28 per ounce. just like that. All right, if you didn't try that example on your own, I really would like you to pause the video and try the next one on your own, and then you can come on back and check that one out. All right, let's do this one together. A 14-ounce box of cereal costs $3.92. If a 16-ounce box of the same cereal costs the same per ounce, how much does the 16-ounce box cost? Oof, there is a lot to that one. But we have to first start out with the information we have. We always talk about things in dollars per amount. We don't usually say you get this much amount for this many dollars. This problem, when we're doing dimensional analysis, can be a little tricky. So let's set this one up the same way we set the last one up. We're starting out at $3.92 per 14 ounces. If we want to figure out how much for 16 ounces, we could set up a ratio. But what I'm going to do instead is I'm going to actually find out how much this one is per ounce, and then I'm going to multiply it by 16 because I think that's the easiest method. So, let's find out. Pause, 1 moment, I need to look and reread the problem. Sometimes I get a little ahead of myself. Oh no, I was right about the ratio. I apologize. I actually am going to set this up as a ratio. So, I want to know how much this costs in dollars. So, excuse me, I'm having kind of a brain fart moment here. Yes, I'm going with my original plan. Thanks for bearing with me. I would like to know how much this is per ounce. So, right now, I've got $3.92 over 14 ounces. If I divide that, I get a number, which I do not have calculated, so let me do that quick. If it is $3.92 per 14 ounces, that means that that box of cereal is approximately 28 cents. It is equal per 1 ounce. And all I did was divide these two numbers. This is where my dimensional analysis comes in. I want to know how much it is for a 16-ounce box. So I'm now going to take this price, this unit price that I have found, and I'm going to multiply it by 16 ounces because that will give me the price of the box. So multiply by 16 ounces, or 16 ounces over 1. My ounces are going to cancel off, and I'm going to be left with the price on the bottom, which in this case, when I do the math, is $4.48, which if I go back and check my actual work, it would make sense that the larger box would be slightly more than the smaller box. Apologies for any confusion on that last problem. I had a brain fart moment, but thanks for sticking with me through it. If you have any questions on this video or any of the previous, please don't hesitate to reach out.